I will do my best to keep this time. So I'm going to talk about the Kodaira vanishing theorem, which is true in characteristic 0 and not true in characteristic p. And I essentially going to talk about the failures in characteristic p. So to state this, so yeah, the basic statement in characteristic 0 is that if you have a smooth projective variety, characteristic 0, and we have an ample line bundle L. So yeah, that means that phi powers of L have a lot of sections, a lot of global sections, enough to embed X in projective space, but you might not know that L itself has any sections. And indeed it might not, but still there's the following vanishing statement that we take the canonical bundle of X tensor with this ample line bundle, then it has no higher cohomology. I say this for k greater than 0. Right. Okay. So when you have a line bundle that has no higher cohomology, then then you can sort of understand easily how big H0 is. So this is a way to produce sections of kind of explicit line bundles. And yes, in some sense, many of the problems in algebraic geometry come down to, can you cook up sections of a line bundle? Can you extend sections of a line bundle from some variety to the whole variety? And so this is kind of an essential tool in algebraic geometry. Okay, so let's see what to say about this. So proved by Kodaira by analytic methods, using Taylor metrics and so on, around 1950. By Kodaira, and let's see what to say. So, so it's sort of closely related to Hodge theory, and although the original proof was sort of not exactly, using related ideas to Hodge theory, but not literally deduced from Hodge theory. But in fact, now I guess in the 80s, by Kodaira and Renault and Lizzie's paper and so on, you can see that it literally follows from the Hodge theory. From the fact that, in other words, from the fact that there's a close relation for complex varieties between ordinary cohomology and coherent sheaf cohomology like this. So in Kolar's proof, what did I write? Sorry, I meant Kolar. In Kolar's version, what you use the fact is that you have a map from cohomology of complex coefficients, so sort of topological invariant, to cohomology with coefficients and X coefficients. You use the fact that that is surjective. So that's a sort of typical consequence of the Hodge decomposition theorem, and yeah, he showed this sort of just this fact that this coherent cohomology group is sort of controlled by topology. That was enough to apply this Kodaira vanishing. Okay, and then another reason to be interested in Kodaira vanishing is that it's, in some sense, the main tool in the minimal model program. So, I mean, slightly debatable, but I would argue that it is the main tool in minimal model program, which is sort of the general framework for classifying algebraic varieties. Yeah, so what to say about them, just to outline this very quickly, that is to say, you want to start with some projective variety, let's say smooth projective variety initially, and then you ask yourself, is a canonical bundle of this variety NF, meaning that the degree of the canonical line bundle on every curve is that non-negative. So the idea is that when you blow up a point on a variety or something, then you create k negative curves for which this fails. So in this situation, we say that X is a minimal model, but in some sense that there's no excess blow-ups. So if you imagine like in some sense, minimal models are the roughly the simplest varieties in their birational equivalence class. There's no sort of excess blow up. And then, you know, the minimal model program says if not, then try to contract some k-negative curves. And so, yeah, what to say? You try to construct a surjection from X to some other projective variety. So this objective where you've contracted some curves that the canonical bundle has negative degree on 2 points, and hopefully in so doing you've made Y closer to being a minimal model. So that's it. So there's So one problem is just to construct this sort of one-step contraction, and this is completely done in characteristic 0 in the 80s. By Kawamata, Shikura, and others, and they sort of fundamentally using Kodaira vanishing and extensions of that. So there are many more vanishing theorems that are useful, like the Cohen-Macaulay feedback vanishing theorem, but that, for example, is a consequence of Kodaira vanishing. So everything kind of goes back to Kodaira vanishing. Yes, and then there's sort of more steps beyond this, like you want to know, well, do I need to do infinitely many contractions? I mean, will I lead to an infinite sequence, or will the process terminate? And so let's say that so much of MMP, but not all, is the conjectures things are known in characteristic 0, and let's say something in characteristic P is known, but only in dimensions at most. So now I'll start talking about characteristic P. So, okay, so in characteristic P, first of all, the Kodaira vanishing theorem is just not true. So Reno showed that Kodaira vanishing fails even for services in any characteristic P greater than 0. So that's quite upsetting. So it's sort of it's sort of possible. I mean, that the minimal model program will work, because maybe you could get by with somehow something weaker than this, but it's not clear like what would be the right substitute. So let's see. Okay, so there's that. Oh yes, and then right, and of course, we know Z proved Kodaira vanishing. And Reno, I guess, proved Kodaira vanishing for many varieties in characteristic P. You have to assume in their statement that the variety lifts to the second bit vectors, or resume on P squared, and the dimension is less than P in one version, but somehow in running the minimal model program, if that's your goal, you don't really have control, I think, about what happens if you start out with some variety, which is kind of nice, but then you start contracting curves. You don't know too much about this new variety, and so it's hard to use these assumptions as far as I know. Okay, so let's see. Okay. So I guess I should say that like the minimal program is almost complete now. For I mean, for services, it's like more or less an old story. It's more or less complete for threefolds in characteristic P greater than 5, and to some extent, maybe, and partly for P equals 5. And just write down a few names by Aiken and Chu, Ricard, Waldron, and others. So somehow in large enough characteristic, we kind of understand this. It's a large body of work, but this the goal of sort of producing a minimal model, or else showing that your variety is birational to a bundle of Fano varieties. That's supposed to be the alternative, and that has been worked out in these cases. Okay, and yes, okay, but why this assumption p greater than 5? Where does that come in? So we use that. So the people's pi version. This is sort of incredibly tricky argument. We should ask why this is by Hagen and Natasha. I won't try to explain their highly tricky maneuvers, but in terms of p greater than 5, they use the fact that we know some vanishing theorems, I guess I would say. So things like that. So KLT, surface singularity, in surface to p greater than 5 is strongly upregulated. So I guess multiple words that I haven't used here. Let me yeah, sort of try to ponder the definitions a little bit. Right. So I guess I want to say that there's sort of local and global versions of vanishing theorems. So I started out by saying that kind of global theorem, but there's also kind of local versions of that, and because of the fact that a typical example of a singularity is a cone over some smooth projective variety. Naively speaking, anyway, you might say that this is sort of the simplest type of singularity. So you take some projective variety and take a cone over that, then sort of that properties like this vanishing theorem for the projective variety translate to some kind of properties about this singularity, and right. That's so strongly irregular some definition maybe about splitting the Frobenius map roughly that that implies sort of good vanishing properties. That's the way I want to think of this. KLT is just sort of this one of the types of singularities that comes up in the mental model program. So I would argue this is kind of the kind of local vanishing statement. Yeah. So I think maybe I need to like pause to think about the definitions a little bit to see like, okay, what is a local, what I mean by a local vanishing statement and what type of singularities am I talking about? So maybe one good formulation is, why don't I say what Cohen-Macaulay singularity, sorry, in a geometric way. So let's say that I have a, so because I want to argue that Cohen-Macaulay singularities are a sort of, it's a kind of local vanishing property, somewhat analogous to this. Okay, so you have a regular Noetherian scheme or whatever, regular outside one point, just to simplify my life, one close point P. Okay, I want to write down concretely what it means for X to be Cohen-Macaulay. There's many other ways to say this. So you could just say that the local cohomology of the structure sheaf supported at this point is equal to 0 for I less than the dimension of X. And then I'll try to translate that, make it even more concrete. Of course, there's other ways to say this, like it's equivalent to your scheme being locally finite free module over some regular ring, but let me use this sort of formulation. Okay. So yeah, to understand what that means, well, what is local cohomology? I mean, it's just the difference between the cohomology of X and the cohomology of X minus this maybe singular point, you know. So we have a long exact sequence. I mean, the definition of local cohomology between, like, say, H1 of XO and H1 of X minus PO, and then H2 localized to cohomology with support, you could say, and so on. The whole long exact sequence like that. And so, right, so Cohen-Macaulayness, the vanishing of this local cohomology group is just, oh, yeah. So let me specialize this more. Let's just replace X by an affine open neighborhood at this point. Which of course is not going to change properties of singular, you know, not going to change whether X is Cohen-Macaulay at this point or not. But if I do that, then the higher cohomology of X with coefficients in a coherent sheaf is just 0. And so the definition of Cohen-Macaulayness becomes just basically a vanishing condition about these cohomology groups. So X is Macaulay, if and only if so I wrote that the cohomology of affine open neighborhood at this point minus the point with O coefficient to 0 for I know it's I from 1 up to n minus 2 and as the dimension of x, and I guess there's some surjectivity part and the global sections of regular functions on x map onto regular functions on x minus the point. So this is just translating the definition using this exact sequence. Okay, but that's basically what Cohen-Macaulay this means. This part is sort of what you would have if x is normal and a dimension at least 2. And so if you have normal variety, Cohen-Macaulay-ness is basically this vanishing. Okay. Right. So hopefully it's sort of clear why I'm saying this. At least I want to make the analogy between this local property and these kind of global vanishing theorems. Okay, so to even be more concrete, you can spell out what Cohen-Macaulay-ness means in the case of a cone. Okay, so take a smooth projective variety, I guess, over any field, and an ample line bundle run it. And you can talk about the affine cone over X with respect to this ample line bundle and ask, what kind of singularity does that cone have? Sorry for my repeating the same picture. The affine code, which is, say, what am I writing? How long? X equals spec of the range of sections of A and its powers. Hopefully, it's clear. So sections of nth power of this line bundle. Okay, so that's what I mean by the affine cone over X with respect to the sample line bundle, and that is Cohen-Macaulay, if and only if just some vanishing theorems on X are true. So it means that the homology of X with coefficients in m times A is 0 for all, it's 0, I between 0 the dimension and m any integer. So, hopefully it's legal that you could pretty easily get from that condition to this condition. Okay, but anyway, so my point is just, you may know other definitions of Cohen-Macaulay-ness, but I would argue that, you can think of it as just a kind of a vanishing theorem for singularity, or in particular for a cone. It just amounts to a vanishing theorem for this projective variety. And this kind of vanishing sort of, like both locally and globally, it's the kind of thing that you need or want to run the middle model programs. For example, if X is so, I don't know, yeah, if X is, I think we was using X and sorry, X for the projective variety, also the cone. Sorry about that. So smooth Fano variety in characteristic 0. 0. And you take let me briefly say then cones over X are, and probably I maybe have to be a little bit careful of which line bundle I'm using. I mean, it's sloppy. And yeah, so cones over X are Cohen-Macaulay, and basically I want to say by Kodaira action. So I don't want to take too much time, but basically, if you have a smooth Fano variety, imagine maybe that A is just the dual of the canonical bundle, so a sort of natural line bundle in that context. Sorry, Fano meaning that the dual of the canonical bundle is ample. Well, then, like, I guess one version of Kodaira vanishing is going to tell you that these cohomology groups are 0 for m greater than or equal to 0 because like n times A is equal to the canonical bundle, which is kind of negative in this case, plus something ample. I guess this will happen if m is greater than or equal to 0. And so that will tell you vanishing these groups for m greater than or equal to 0. On the other hand, if m is less than 0, then it applies Serre duality to Kodaira vanishing, and it also tells you that these groups are 0. Yeah, so, and it's less than 0, and all the way up to the dimension, these cohomology groups are 0. If you have Kodaira vanishing. So, right. Okay, and let's see, a generalization of this fact is that, so here I'm just talking about cones, but there's, not surprisingly, there are versions of this statement, of this implication for general singularities that are not just cones. So every ELT, Cohen-Macaulay terminal singularity characteristic 0 is Cohen-Macaulay. And this is a sort of like basic, useful fact, and then a lot of it. So I will probably write down the definition in a second, but maybe just the intuition is that a KLT singularity is basically the cone over a finite right. I mean, sorry, if it is a cone, then that's what KLT means. Yeah. Okay. So right, and then the idea is that this is again sort of using Kodaira vanishing or suit depth versions of that. And again, this is something which is just not going to be true in characteristic P. I see. Oh, maybe that's not obvious though, because so I mentioned that Kodaira vanishing is not true for varieties in general in characteristic P, but for this kind of question, because we're roughly looking at cones over Fano varieties, the relevant question is whether Kodaira vanishing holds for Fano varieties. But unfortunately, even that's not true. Okay. Examples earlier that so for every t greater than 0, there is a smooth Fano variety, let's say over FP, for which Kodaira vanishing fails. So there's some ample line level for which this desired property fails. And what can I say? So it's sort of different from Raynaud's examples, though, in the sense that in these cases, by the examples, the dimension is getting bigger with P. So like it's the dimension of X with something like Y is 3, or dimension 5, I think it's equals 2. So
Sorry, what's the degree in which it fails?
I'm not going to remember. It's probably either H1 or Hn minus 1, but I'm not sorry. So, yeah. So okay, just maybe to describe like what sort of examples these are, like what varieties these are. In some sense, you want like varieties that have sort of strange characteristic P behavior. So there's a lot of options for that. But the one that I used here was so we used varieties like P, perhaps, where we use a semi-simple, even like split group over a P or a P bar, and P is a non-reduced, so to speak, non-reduced parabolic subgroup. Subgroup scheme with yeah, so not reduced, but with reduced locus, a parabolic subgroup.
Examples of vertices, you know, some of
oh yeah, I mean,
I to the power P.
yeah, that's right. So I mean, I should write down some more names like Habush and Martin studied these varieties before. I think sort of.
Yeah, Loritza. I was thinking of you.
No, yeah, of course, you're right. There's a long history.
Okay.
Okay. Right. So anyway, so there's this kind of example, and yeah, if you translate well with a bit more work, you could cook up terminal singularities in any characteristic. Well, so what would be the sort of local analog of Kodaira vanishing? It's this Cohen-Macaulay. So for every so in this case, we have to look at Yasuda is always P. For every 0, there are terminal singularities in characteristic P that are not coherent. I mean, like over FP, say. Yeah, so and again, the examples that we have are sort of with dimension increasing with p, which is not as strong as one might like. So dimension roughly p, I guess. Yeah, so yeah, it'd be nice to know what happens in a fixed dimension. I mean, yeah. So anyway, like one way to get examples is just to take a suitable cone over this kind of special, weird projective variety. Maybe I should add, like, this is a smooth projective variety. In some ways, very simple. It's rational. It has a affine cell decomposition, despite this p being kind of weird. And yeah, but nonetheless, it has this kind of strange behavior. So cohomology. Right. So sometimes you can take cones over those varieties and get terminal singularities that are not Cohen-Macaulay. You also had a different idea, which is to just take linear, what would they be called, like quotient singularities. So he just used vector space mod G, where G is equal to mod P, and B is just a finite dimensional representation in characteristic P. So of course, representation theory for the group C mod P and characteristic P is more complicated than characteristic 0. But in this case, for such a small group, you can classify all the representations of to isomorphism, and in some cases, he was able to argue that you get something which is terminal and not Cohen-Macaulay. But again, with sort of dimension bigger than one might like ideally. So yeah, I mean, a question that comes up is like, what happens in a fixed dimension? So question, well, number one, which I don't know how to address, but which is sort of, in the background, like why we're interested in these things. So like, could the model program actually fail in small characteristics? So for 3 folds in characteristic 2 or 3. Maybe there's, so many things are more complicated than characteristic P. It would be nonetheless a shock if the whole mental model program failed to work in some case, but yeah, we don't. That's one reason for being interested in finding examples of weird behavior in characteristic P. What does it mean? Well, I mean, you want to show that basically, like, any variety is birational to either a minimum model or to a bundle of Fano varieties. That might just not be true. Or there are other concrete things you could say, like for any smooth projective variety in characteristic 0, the section ring of the canonical bundle is a finely generated algebra, and that might not be true in characteristic P. So yeah, there's sort of concrete things you could ask. But that might not be true. Okay. Right. So number 2, yeah. So it's like in a fixed dimension, some dimension, each dimension n is a number t0 depending on the dimension, such that say KLT singularities, sort of singularities in the model program, and maybe it's about time to write that definition in dimension n in characteristic P, at least this number, are going to. So, I mean, yeah, perhaps the model program works roughly as we expect in any given dimension, but at least for sufficiently large terms. And that's not known, except in dimension 3, something like that. So yes, to in dimension 3, I've taken Vitashek with few names, and then in a more precise form by Orbitz and Bernasconi and Lazzini. So let me put their statement over here. those three authors, let's see, so KLT singularities of dimension 3 are Cohen-Macaulay in characteristics be greater than 5, but not in smaller characteristics. Maybe I should say over a perfect field of characteristics greater than 5, but not, or the counterexamples in characteristics 2, 3, and 5. Okay, so obviously this has something to do with, it's not literally, I mean, it has something to do with the fact that the middle model program works better in characteristics greater than 5 in dimension 3. Okay, sorry. So I guess maybe putting off defining this thing. So let me quickly define it. So a normal variety defined quickly, as you've all seen before in talks, perhaps define these classes of singularities in the minimal model program. Normal variety, let's say it's called terminal, which is kind of the simplest type of singularity that you need to consider if you're going to expect to have minimal model for varieties. Yeah, you can't expect, so in dimension 2, a surface, either it's rational, or it's a bundle of, or it's a ruled surface, or it has a minimal model, and that minimal model is smooth. But in dimensions at least 3, the best you can hope for is a minimal model with terminal singularities. Okay, so meaning if so you can use the canonical class X is not it's not smooth, but you still have a Bay divisor representing the canonical bundle kind of on the smooth locus. If some positive multiple of that is Cartier, and for a resolution of singularities, what am I pi from x tilde to x, the canonical bundle of x tilde is the pullback divisor of x. So this pullback somehow makes sense because of this assumption, plus a positive sum like this. Greater, these are rational numbers because of this Q here, and they should be positive for every exceptional divisor. So exceptional means you look at all the codimension 1 subvarieties that map to something of lower dimension in X. That's what exceptional means. And so all those divisors should occur here, and they should all have positive coefficient. Okay, so what does this mean? This has sort of quite simple intuitive meaning, I would say. What this says is that if you have differential forms, like n forms on your n-dimensional variety, and you try to pull them back to resolution, because X is singular, it's not obvious that what you get is actually a holomorphic section of this bundle. It might have poles. When you try to pull back, you might get something that has poles on the exceptional divisors. And this condition is precisely saying that you pull back a differential form, it has no poles, and in fact, more than that, it actually vanishes on these exceptional divisors. So it's kind of saying that your singular variety behaves like a smooth variety in the sense that you can pull back differential forms, and it behaves the way pulling back differential forms does on smooth variety. Okay, so and then quickly, KLT is a sort of a broader class that also can be used in the model program.
So is it clear that this condition doesn't depend on pi?
It's not obvious, but it is true. So, right, and basically the reason that it is independent of resolution is exactly the fact that for smooth varieties, you can pull back differential forms and you don't make any. So you can sort of compare one resolution to another. Okay, right. Okay, so yeah, so I guess. So one interesting thing, even if you don't want to follow all the details, is just, you know, what are the weird examples that are coming up here? So saying like, oh, examples by ABL, yeah, Arvidsson, Bernasconi, Lazzini, and also Cascini and Tanaka. These are sort of, how do you produce weird singularities in dimension 3? Roughly speaking, you want to take something like a cone over a weird surface. So are based on strange pencil surfaces, yeah, essentially that, maybe singular. So I'll just give one other example. So like in characteristic 2, what's an example of a strange pencil surface? You can start with sort of characteristic 2, you could start with P2 over F2. And then you could blow up the 7 rational points. 7, okay, so blow up the 7 points P2 of F2. Right, and then what happens? Well, then you can contemplate all the F2 lines. Of course, the line's not going to go. The line is going to go through 3 F2 points, of course. So something like this. And then I want to say, and then contract the 7 lines divided over F2. So the point is that after you've done this first blow up, then these lines become disjoint from each other, right? Well, at this point, then these 2 lines are disjoint, and so you can contract 7 lines and get, rather not too complicated looking surface. So you get a Del-Pezzo surface with canonical singularities or dual singularities with 7 nodes. And this is the point is that this is a surface which sort of, so to speak, only exists in characteristic 2. And somehow, because of that strangeness, I mean, obviously, you just don't have this arrangement of points and lines in any other characteristic. And let's say some vanishing theorem like come out of p-adic vanishing fails on this. And then somehow you can take something like a Cohen to produce these kind of weird threefold singularities in characteristic 2, I guess. And then there are sort of similar but more complicated weird Del-Pezzo surfaces in characteristic 3 and 5. So let's right. So what I want to do is my sort of pre-theorem is just to I basically want to find the worst possible examples in characteristic P. So in dimension 3, this is we have these kind of weird examples with one type of singularity, but I want to make these singularities as mild as possible. So there are terminal singularities, just mild condition which you just can't avoid in the middle model program. At dimension 3, that are not Cohen-Macaulay, if P is 2, 3, or 5. Yeah, so maybe I'll just add that there's a kind of mixed characteristic version of this, I guess also pre-theorem. So likewise, there are such examples in mixed characteristic 0p with p equals 2, 3, or 5. So now the notion of terminal singularities and of course Cohen-Macaulayness makes perfect sense in mixed characteristic. So what I mean is if you have to contemplate what I mean by dimension 3 in this mixed characteristic case. I mean, we're talking about schemes of dimension 3. So this is the regular, sorry, maybe not regular, but scheme of dimension 3. So the kind of thing that I'm claiming to exist here is a scheme of dimension 3 with a flat morphism to stack of the p-adic integers. So these fibers are 2-dimensional, such that there's some isolated singularity, which is terminal singularity, but not Cohen-Macaulay. Okay, so
is it always isolated singularity? Consider.
I mean, the examples, yeah, I mean, I guess actually, yeah, if I want terminal, that implies that the singularities have co-dimension at least 3. So in this case, they would have to be isolated. Yeah.
In this case, how do you define K?
K.
How should I interpret K?
Oh, yeah. So I mean, you can just think of it as the relative dualizing sheaf over this. So right. So yeah, I mean, so there's sort of 2 questions. Since this was sort of the main thing I want to present is this example. one thing is just how do you define these kind of weird varieties, and the second question is how do you prove things about them. I mean, obviously, it's good to understand what this variety is before I get to proving anything about it. Okay, so so what are these examples? I would say it seems like they're definitely not cones. I mean, any singularity, you know, has some sort of relation to cones, but it's not exactly a cone. How to do it? I think the simplest one is the one in characteristic 2. So in characteristic 2, we can take singularity to be product of 3 copies of the affine line minus the origin divided by the action of the group of order 2. And I just take about almost the simplest action you can think of, the action by this group generated by an element sigma, sigma of like x naught x1 x2 is 1 over x naught 1 over x1 1 over x2. Okay. So that's it. You take this really simple variety, divide up by this action of this group, and you get this weird singularity in particular. It is terminal, but it's not. So maybe to comment about this, like, so in a sense, you could say this is a quotient singularity, but quotient singularities in characteristic P are sort of totally different when the group has order multiple of P than what you're used to in characteristic 0. So particular, just trying to muse about this kind of thing a bit. How should I put it? Let's say there are sort of large continuous families of different actions of Z mod P on, say, smooth varieties in characteristic P. So, I mean, for a finite group of order like prime to P, if it has a fixed point, then the action is linearizable around that point. It's locally isomorphic to just a linear representation of G. But in this case, that action is definitely not linearizable. Oh yeah, and then I guess sorry, the singularity is the point 1, 1, 1. It's the fixed point for this. Right. So yeah, how can you know that this is not linearizable? Well, just because there's an isolated fixed point. So for any representation, the group, any non-trivial P group in characteristic P, I guess I want B not to be 0. It's always true that the subspace fixed by G is not 0. Because the only reducible representation of V in characteristic P is the trivial. And so what that means is that if you have, in this geometric situation, if I have a finite group, I mean Z mod P, acting on a smooth variety in characteristic P, with an isolated fixed point, then it cannot be equivalent to a linear action. Right? So a linear action, there's always this non-zero subspace fixed by G. Whereas here, what we have is a threefold with an isolated fixed point. So it's not linearizable at the very least. Why sometimes why not for this threefold is definitely not so not only are I was sort of saying here that actions of a finite group P group in characteristic P, not only are they not linearizable usually, but as I say, there's lots of sort of non-equivalent ways that a group like this can act.
Like this only in dimension 2. So if you try to construct this example in dimension 2.
Right. Well, so you're not going to get the same phenomenon in characteristic 2 for a sort of silly reason that so all the varieties that we're talking about, like when you take a quotient by a finite group, you get a normal variety, and the thing is that a normal variety of dimension 2 it is automatically Cohen-Macaulay. So yeah, so other sort of properties can go wrong. Like yeah, sort of strongly F regular is a stronger property, which does go wrong for some nice looking singularities in characteristic 2, but like Cohen-Macaulay, I guess, is going to be okay.
Question, is it interesting to replace A1 minus 0 by an elliptic curve?
It probably is, yeah. Let's see. Yeah, I mean, just get some different singularity at that point. Yeah, I think I don't have anything special to say about it, but in some cases that might be better. Okay, so right. Okay, yeah. So then when I sort of outline like, okay, so why does this example have strange properties? So let's see. The fact that it's not Cohen-Macaulay is relatively easy. So Oversea showed this is let's see, 81, I think. If you take a regular scheme over FP and G, let's just say cyclic triple order P acting on Y, I guess, a regular scheme, but cyclic triple order P acts on Y with, let's say, an isolated fixed point. And suppose that Y has dimension 3, so I don't run into this, then this quotient singularity is never Cohen-Macaulay. So this kind of, so to speak, wild quotient singularity is essentially never Cohen-Macaulay. And so, yeah, so just in the fact that this is an isolated singularity, we know that this quotient thing is not going to be Cohen-Macaulay. Yes, I wanted to say something about maybe just like why is that true? Over this result. Yeah, so let me put it like this. So basically, proof to sort of sketch in a few words is that we want to show that this quotient is not Cohen-Macaulay. We want to arrange that to show that H1 of this singularity minus the singular point itself with O coefficients is not zero. As I explained, Cohen-Macaulayness would mean this kind of vanishing. But why is this? I mean, essentially the reason is that the group is not zero because the cohomology of G sort of contributes to this. And of course, cohomology of Z mod P, you know, if we're in coefficients in a field of characteristic 0 would be 0, but in characteristic P, the cohomology of G contributes to this. So specifically, the cohomology of G acting on the functions on Y, there's some spectral sequence that relates this kind of group to that kind of group. So, I mean, this kind of idea goes back maybe to Sarah's examples about like when you take quotients by Z mod P in characteristic P, that contributes to the coherent cohomology of your variety. Okay, so yeah, there's more to say, but let's just leave it at that. Okay, so and then the other question is, so somehow, yeah, it's sort of easy that this kind of singularity is not Cohen-Macaulay, and I guess what would happen is that if you took sort of more complicated examples of Z mod P acting on smooth threefolds in characteristic P, they would usually not be terminal or anything like that. So in general, quotient singularities, or they should call quotient singularities because they're sort of different. Quotient singularities in characteristic P need not be terminal or even this weaker property ALT, canonical. So the idea for this example is you have to somehow think of what's the simplest possible action of Z mod P in characteristic P that has an isolated fixed point. And so we're just, my intuition is that this is the simplest, but anyway, that's how you, so you need to choose a simple example and then hopefully you can show that what you have is terminal. So let's say to show that my mod G is terminal, I don't have any sophisticated way to do this other than just resolve the singularities and compute. And this is why I have a pre-theorem. So in some cases, I mean, in this case, in characteristic 2, everything works out. But in general, resolving these singularities is kind of painful. But I'm confident that with time, it will happen. In this case, it does work. So yeah, to check this condition of terminal singularities, you have to. Sometimes you have to look at. You know, to say brief picture of what the resolution looks like. So yeah, so how do you resolve somehow? It's a kind of computational problem, but you got to sort of minimize your work as much as possible. So the way I approached this was to try to make a G equivariant resolution of this blow up of this smooth variety. How am I writing this? Yeah, so if I call y0 be this three-dimensional smooth variety over F2, let y1 be the blow up at the origin. Sorry, at the fixed point. And yeah, so then what you produce is instead of having just this one singular point and why not one G? So let's draw why not. You have this exceptional divisor, it's a little easier, which is like P2 over F2. And then a convenient fact, I'll just write down some names, is that it's sort of very easy to tell when some of the issues you could, okay, y is already smooth, and the group G is acting on it. The question is, how much do I need to blow up y0 in such a way that the quotient variety becomes smooth? You prefer to do that without actually like finding the equations for the quotient variety, and there is a very convenient result about that. So, like, if you have z mod p acting on a variety in characteristic p, so let's say regular scheme in characteristic p, and if the fixed point scheme is a Cartier divisor, then the quotient variety is regular. So that may look a little mysterious, but basically the fixed point scheme is a kind of very obvious sub scheme to write down. You just write down the equations that say that some point is fixed by the group. Yeah, but somehow the idea, so what this theorem says is that it's sort of very easy to check whether a quotient variety is regular just from looking at the original approach. Just to outline this briefly. So what happens in this example is that when you blow up the first time, you look, okay, so what is the fixed point scheme of y1 as a set? It's this divisor here, this p2, but as a scheme, it's kind of like this p2. So y1g is as a scheme, it's p2 over f2 with some non-reduced stuff at these 7 special points. So reduced, that's p2 of f2. Okay, but fortunately, so that means that when you take the quotient, this theorem is probably almost if and only if when you take the quotient, you get a surface, or sorry, a threefold with 7 singular points. But then you just blow up one more time, and yes, so after you blow up one more time, you get a P2 with 7 other P2s sticking out of it. This is Y2, and then it happens that in that case, the fixed point scheme is a Cartier divisor, and this thing is so it is a resolution of singularities of our original variety. Let's say 1 minus 0. Okay, of course, producing resolution of singularities is one thing. You need to do a kind of computation to check that it's terminal, but that's sort of the easy part. Okay. So to finish, let me just say, so I was claiming that there are examples like this in a few other cases. What are the examples? So examples in other cases like mixed characteristic 2, 2. So again, let's see this in Fogarty's theorem. This is about varieties over FP. So this doesn't immediately imply, but nonetheless, by this kind of argument, I guess it's easy to show that it's often easy to show that quotient singularities are going to be not Cohen-Macaulay. The issue is how to arrange that they're also terminal, and you can do that just by finding a good example and blowing up. Just do some work. So an example is take my line be the set of points I, x, y, and A3 over F3 such that I squared is minus 1 and x is not 0, y is not 0. And right, so then so that's a what is it? It's a this is a scheme. It's I guess a regular scheme of dimension 3, right? So sorry, I meant to say, oh, sorry, I'm talking about Z2. Sorry. So yeah, affine tree space over Z2 is a 4-dimensional scheme, but I have this equation, so that makes it a 3-dimensional scheme, and it's flat over Z2. And basically, I just want to imitate that example. So again, the idea is I just make the simplest example that I can with an isolated fixed point. So it's act on y by sigma y equals minus I 1 over x 1 over y. And again, sort of the same thing happens. So again, this is a 3-dimensional, sort of like the previous example. This is a 3-dimensional scheme, but now living over spec of F2. And for this group action, there's an isolated fixed point, which is only in characteristic 2. So again here, my G is terminal Cohen-Macaulay. And yeah, just to say the other basic properties, it has dimension 3 and it's flat over C2. So, I mean, naively, you might expect that having this example in dimension 3 in characteristic 2, you could make an example. There'd be like a 4-dimensional scheme over a family of 3-dimensional schemes over Z2. But in fact, you can get down to this dimension by this little trick of I goes to minus I. So yeah. To describe this story briefly, like the resolution you construct of this singular scheme, mixed characteristic looks exactly like what happens in characteristic 2. So yeah, that kind of exceptional divisor.
Could you do square root of 2 instead of I?
You could, definitely. I found that this gave the simplest equations that I could. So I just tried to make the simplest equation. So I'm supposed to conclude on time. So so you're sort of like, if you want to make similar examples in characteristic 3 or 5, it means you have to sort of find the simplest examples you can of group actions. I'm going to use Z mod P. Let's say over FP. So act on characteristic 3. I just use Z mod 3. Say Z mod 3 act on this thing over F3. By I guess just sort of permute the variables in x, y, z, goes to y, z, x, say, and sort of translation action here, like x, y goes to x plus y or something. Hope I'm writing it down the right way. Yeah. So yeah, again, you can write down a pretty simple action with an isolated fixed point, and then everything works. So then you get terminal singularity, not Cohen-Macaulay, dimension 3 over F3. And so finally, just in characteristic 5, it's somehow harder to guess what the simplest singularity is, but I'm pretty confident that this would take Z mod 5 acting S times P1 over F5, where S is the quintic Pelpetzo surface. E2 blown up at 4 points, you could say. If you describe it that way, it's not obvious that that the surface has an actual Z mod 5 on it, but it does. The automorphism is S5. And you can think of that, if you like, by doing this as the modulus M05 bar, moduli space of curves of genus 0 with 5 marked points. So what happens for this group action is that, so in characteristic 5 and only there, this fixed point set of z mod 5 acting on the surface is just one point. And yeah, and so on S cross P1, there's just one fixed point in characteristic 5. The quotient is definitely not Cohen-Macaulay, and let's just say expect this surface, or sorry, this threefold is terminal line Cohen-Macaulay. Just to write down the setup, this is dimension 3 and over. Okay, let me stop it. Thanks. Thank you. Questions?
Yeah. Can you say again, maybe I missed something in the chain of, so this proven NP low artistic and low dimension?
Well, it depends what you want to disprove. I mean, so these are examples showing that, some vanishing theorems, don't hold in low characteristic in dimension 3, but the whole minimal model program, might be true despite this. It depends.
This is a question. So you do not
I'm
show
not
that there is one example where there is no minimal model.
No, not that. Let's say that would be bigger.
Oh, okay.
Wait, is it possible to describe what stable curve a fixed point is?
But, oh yeah, of course. I mean, it's point yeah, good question, I guess. You take the point in M05 R, which is represented by key points, so 0, 1, 2, 3, 4 on it. So, just to explain, these are all the points in the affine line over F5, by the way, I think this is. So how does a group Z mod 5 act on this moduli space? It acts by renumbering these you have points in P1 and you renumber them by a cyclic permutation. So that means that the way this group Z mod 5 would act is it would turn this into the arrangement of points, like this is now P1, this is P2, sort of cyclically permute by 1. But the point is that in characteristic 5, those two arrangements are equivalent by just translating by 1, because 4 plus 1 is so that's the point.
So this Z-mod 5 action only on S, or you also do it on?
Oh yeah, I mean, sorry,
translation?
is this translation? Again, it's weird because it's kind of like just trying to guess what is the simplest action. There's some evidence that that sort of points to these things being the simplest. Maybe I'll just briefly say that, like Michael Arden studied quotient singularities in characteristic P, and so what you find is that like P2 mod this over F3 divided by Z mod 3 has an E6 singularity, which is a lot more complicated than you would expect from characteristic 0. But the point is that it's the simplest that could happen in characteristic 3. And so there's a sort of reason to think that that this is like the simplest way Z mod 3 can have a fixed point on the surface in characteristic 3. There's sort of a similar story here. Like, I guess in this case, if you take S Z mod 5, this has an E8 singularity in characteristic 5, which again, it looks complicated if you use characteristic 0, but that's the simplest that could happen in characteristic 5. So yeah, there's some evidence that leads you to these examples.
And how do these properties of like KLT and terminal behave with respect to like taking hyperplane sections? Is there a hope of getting lower dimensional examples by?
Yeah, I mean, that's so you couldn't really produce examples lower dimensions than this, but in general, that's an actual question, and the answer is that it's sort of, as far as I can understand, it just doesn't work very well in characteristic P. In characteristic 0, like intersecting with a general hyperplane section works great for these singularity properties, but in characteristic P, not, essentially because it's like the way the Bertini theorem fails. You would like to say that we have a map between smooth varieties. The inverse image of a general point should be smooth, but in characteristic P, that's just not true. So, yeah. So the answer is that sort of argument. It's very tempting, but it often doesn't seem to work.
Sorry, this is just a naive question that maybe already can be answered from your examples, but can you say anything positive at all? Like if you have a terminal singularity, like basically at least like universally catenary or something.
Oh, I see. Well, I mean, I'm talking about, think about, let's say, varieties over a field or something. Yeah, I think the varieties, they're singularities, we're talking about much milder properties than you're talking about. Yeah, what can I say? Are there good properties? I mean, these are normal, otherwise I don't know. I mean, it could be that, you can imagine like, Kodaira vanishing theorem is not exactly true, but those cohomology groups are kind of small in some sense. Maybe that would be enough for the normal program. But of course, it's just hard to think about what the right thing.
All right, in the interest of time, I declare